So, have you ever really stopped to think about how a machine actually learns? I mean, how does it go from knowing absolutely nothing to making predictions that are, well, pretty smart? At the heart of it all is this beautifully simple question. How does a machine sift through an infinite number of possibilities to find the single best answer? Okay, let's get into it.
Right. So imagine you've got this scatter plot, just a bunch of dots, and your job is to draw a straight line that best fits that data. Now, you and I could draw a few, but a machine could draw millions, billions, technically an infinite number of lines. But only one of them is the best fit. The machine is basically on a quest to find that one perfect line. But how does it even know where to start looking?
Well, the answer is a really cool process called optimization. And don't let the fancy word fool you. All it really means is searching for the best possible solution out of all the available options. For our line fitting problem, best means the line that makes the fewest mistakes, the one that's the least wrong.
To find that least wrong line, we first need a way to measure just how wrong any given line is. And this brings us to a really powerful analogy that I love to use, picturing it all as a giant valley of errors.
This measurement is handled by something called a cost function. You can think of it like a strict scorekeeper. For any line we draw, the cost function calculates its total error, usually by looking at how far away the line is from all the real data points. So for every single line we could possibly draw, this function gives it a score. A high score, or a high cost, means that line is a terrible fit. A low cost, well, a low cost means we're getting closer.
And here's the cool part. We can actually visualize this. If we were to plot the cost for every single possible line, we get this massive bowl shape, this valley. Every single point inside this valley represents one specific line and its error score. And just like that, our quest has a clear destination. We need to find the absolute lowest point in this valley, because that spot, right at the bottom, represents the line with the minimum possible error.
Okay, so we have our map, this huge valley of errors. But let's say we're just dropped somewhere randomly on its slope, and it's foggy. We can't see the bottom. How in the world do we know which way is down? We need a compass.
And that compass has a name. It's called the gradient. Now, in calculus terms, the gradient is just the derivative of the cost function. In simpler terms, it's the steepness of the valley right where we're standing. But here is the most important, kind of counterintuitive part. The gradient always points in the direction of the steepest uphill climb. It tells you the quickest way to make your error even worse.
And this is the big aha moment of the whole process. If our compass, the gradient, is pointing straight up the hill, what's the most logical way to go down? You just turn 180 degrees and take a step in the exact opposite direction. It's that simple. We figure out which way is up, and we take a step down.
So we've got our direction figured out. The next obvious question is, okay, but how big of a step should we take? Because it turns out the size of our step is just as critical as the direction we're heading.
This is controlled by a little number called the learning rates, which you'll often see represented by the Greek letter alpha. And it's nothing complicated. It's just a small number that we choose to decide how big our steps will be as we walk down the slope of our valley.
But you've got to get this learning rate just right. It's a real Goldilocks situation. If your steps are way too small, sure, you'll get to the bottom eventually, but it's going to be a slow, tedious crawl that could take forever. On the other hand, if your steps are too big, you might literally leap right over the lowest point and land on the other side of the valley, just bouncing back and forth without ever settling at the bottom. So all this logic, knowing the direction and knowing the step size, can be wrapped up in one simple, elegant formula. Our new position in the valley is just our old position minus our learning rate multiplied by the gradient. This one rule, this update rule, is the engine that drives the entire learning process forward, step by step. Okay, let's put all the pieces together now. Let's watch this beautifully simple algorithm perform its magic. Let's watch the descent in action. Just look at this table. With each step we take, each iteration, our cost, which is just our error, gets smaller and smaller and smaller. We start with a pretty high error of over 250, but after just 10 steps, it's already down to 112. After 100 steps, look at that. Our error is down to a tiny 2.1. The machine is literally learning before our eyes. So really, this whole thing is just a simple loop, a recipe. You can see it laid out right here. First, you start with some random parameters for your line. Then, you calculate the cost. You figure out the gradient, which way is uphill. You take a small step downhill using your learning rate.
And then you just repeat. You keep going step by step by step until your error stops getting smaller. That's it. That is the gradient descent algorithm.
And here is why this matters so much. This simple idea of walking downhill isn't just for fitting straight lines to data. Not even close. This is the fundamental training algorithm that powers some of the most complex and powerful systems in modern AI. From the huge neural networks that recognize faces in photos, to the recommendation engines that know what movie you want to watch next, this process of gradient descent is the engine working tirelessly behind the scenes.
Now, for this whole explanation, we've been exploring a nice, simple valley with one clear, obvious bottom. But what happens when the landscape gets more complicated? What if there are tons of different valleys, each with its own low point? How does our algorithm know if it's just stuck in a small ditch, or if it's truly at the bottom of the Grand Canyon, the one true minimum? Well, that is the next great challenge in the world of optimization.